numbers that you should have gotten. Questions? A, B, and C. So please make sure you're looking at the correct ones. All right. So we'll go with version A. Here are the rest of the answers for the next 4 questions on your test. This is for number 3, should have had 12.2 psi. For number 4, should have had 159 kPa. For number 5, your line should have been curved and going up. For number 6, your line should have been straight and going down. Anyone with version A have a question on that? Version B, ladies and gentlemen, okay? Your first line on your graph on number 1 should have been straight and going down. Your pressure in kPa should have been 103. For number 4, the line should have been curved and going up. And for number 5, you should have had 9.96 psi. Questions on that one? Okay, and then finally, ladies and gentlemen, version C. Should have had 176 kPa for number 1. The graph should have been straight and going down in number 2. The graph should have been curved and going up in number 4. And your pressure in number 5 should have been 11.9 psi. Questions on any of those? All righty. All right, ladies and gentlemen. So here's what I would like you to do. In a minute, you are going to go to one of the 4 lab tables. And when you get to one of the 4 lab tables, ladies and gentlemen, you are going to be working with whoever else is there with you. At the middle table in the back, ladies and gentlemen, there is a setup that looks like this. A book of matches, a beaker, and a Petri dish, 3 coins in it, and a candle. You are going to take and you are going to go to one of the 3 tables. One of the 6 lab stations that is out there. Stack the 3 coins in the center of your Petri dish. Put the candle right in the center of that. There are pitchers filled with water at every table, ladies and gentlemen. You will take that pitcher and you will add water to this dish so that it is below the level of the candle, but up quite a ways in the container. So you would almost filling the container totally up, but the candle is sitting high enough that it is still above it. You will then, ladies and gentlemen, take a match and light your candle. Please remember, after you light your candle, blow your match out, throw it in the metal cans that are at each station. What you are then going to do, ladies and gentlemen, is you are going to take this beaker, you are going to invert it over the top of the candle, just like this, and you are going to make observations of what happens. And I want you to think in terms of gas laws. You are changing a variable in this demonstration. The variables are pressure, volume, amount of gas, and temperature. And you are changing one of those variables, which causes another one to also change. Now, we are specifically talking about the gas inside the beaker. So you have to pay close attention to what happens to what is going on inside the beaker in this experiment. And as a group, you need to explain to me what has happened in terms of the 2 variables that changed and how one caused the other to change. Questions? Now, I will give you one more hint ladies and gentlemen, and that is this right here. This is a activity, oops, where we are burning an organic fuel, the candle, a carbon-based candle. Now to burn, we need oxygen, and we create carbon dioxide gas, and we create water as a liquid. So, I didn't say that. Why? So what am I changing? How am I changing the pressure? Boyle's law is pressure volume. You got to tell me. This is the helpful hint that will help you understand what is going on. I want you to pay close attention. There are only two gases involved in this. Remember, we're talking about gas laws here. A solid does not affect gas laws. A liquid does not affect gas laws. Only gases are affected by gas laws. Go get set up. Go get done, ladies and gentlemen. Start coming up with an explanation for what you see. You can work in group of up to 4 people at a lab station. There are 6 setups there. Make sure everybody is at your table before you get going. Please do not burn your hair in this experiment. I would hate to have to use the fire blanket to smother you. The water needs to be below the level of the candle, otherwise the candle will not burn. Let me know. You're welcome. As soon as your group is ready, yeah, you can go.
Do we have to put water around it?
That was what I did up there, yes. Remember, the water needs to be in the container almost filled, but not over the top of the candle.
Use another one. We don't have a can.
You don't have a can. Other than the one that's right there at your station? No, you probably don't.
Why did you say it? Oh, ours went out.
Okay, that's not about gas laws, though. Think about gas laws. What else happened in your experiment?
Water and fire.
Again, you and your partner, explain to me what happened based on the observations you saw.
Okay, so do we have to restart?
No, you should be able to do it once, and you should be able to come up with an explanation. Remember, your explanation says that this variable changed and this variable changed. Changing meaning they went up, they went down. What variables changed in this experiment? Again, remember, we're talking about the gas inside the upside down beaker. What happened to the gas inside the upside down beaker?
I don't think volume changed at all, and neither did amount. So temperature went up. Pressure. Does this have to do with gas laws? Yeah, this is like the gas laws we want.
Maybe, maybe not.
That's not awesome. It's yes or no.
Okay, no.
What?
This is about what you saw happen here.
Yeah.
So, what variables changed in this experiment that caused what you saw happen?
I thought it was pressure.
That sounds like
That makes no sense. For real. He makes no sense.
Wait, you said it was a gas loss.
I said this is involving gases and the four variables that we have talked about. What two variables changed in this lab that you saw happen in the beaker? What two things changed? Because you can't only change one. So there had to be two things that were changing, because if one thing changes, something else had to cause it.
No,
No, I think.
So as a group, you should tell me what variables were involved and what changed. Did it go up? Did it go down? So this variable went up. This variable went down. And I know this because here's what happened inside the jar. Okay, so what do you got?
Yeah, because that's the. I think
Okay. So what else changed?
Because you're heating the air, right?
Okay.
What
signs
do you have that temperature and pressure change? So that's why
Okay. This temperature will cause the water to lift up.
it's Charles' law.
I said it was Boyle's law.
It's Boyle's law.
Oh, wait, no, I think he's trying to teach us all the laws combined.
Pressuring, putting pressure. Thank you. Thank you. She just had the same look on her face I did on mine. Like, what in the hell are you talking about? How are we putting pressure on you? How are we putting pressure on you? No. The gas is already inside there.
Okay,
That's what we should be talking about, because we're in the gas law unit. So what variables about the gas inside there changed? Okay, so the water got sucked up, so what did that change in?
No, I think
What did that change in?
It changed exactly what it changes. It's volume and
Because
temperature.
as the water gets
What are you guys doing?
it's changing the amount of volume. So it looks like.
You just need to know what.
It's not like having this pressure like that much, you know what I mean?
Okay, how do you know temperature, volume changed in here?
Because the
Well,
temperature
those were already there, that didn't change.
and the volume of the water, the volume in there. I don't know how to explain it. It just makes sense in my head.
Yeah, it took up more area.
Okay, so let me ask you this. What happened to temperature in there?
It was trapped.
What happened?
Yeah.
Temperature,
It went
Temperature
up.
can't be trapped. Things either go up or they go down. So if you're saying the temperature changed, okay, so what should happen to volume?
I think amount makes sense.
What? Should go up. So did the volume of the gas inside there go up? And if it did, how can you prove that it did?
Yeah, but I can't do the experiment stuff.
How, what observation can you tell me that
The gas went up to the top of the can.
wasn't there gas up there already?
It's not before you put the can.
Really? So you're telling me when I turn this over, there's no gas inside there?
Should we
Right?
try it?
I told you not to put me on the spot. It makes sense in my head.
Okay, and I'm just working through it. If you're telling me something changed, something else has to change. Gas law says that if you change temperature, volume will do what?
So it does have to do with the gas.
No,
What?
it can have to do with gas laws. Gas laws explain everything. Stop, don't do it again, just listen. Because I want you to listen. All you're doing is playing when you do it again. If you want to do it again, you can do it in a second. But please listen. If you are telling me that temperature goes up, and you're saying that it's a relationship with volume, what does volume have to do if temperature goes up? Volume has to go up, which means the gas inside there has to take up more space. Correct? That's what volume going up means, right? Okay. So if the volume in there is taking up more space, think about what that would mean for the gas, because when you turn it is full of gas.
Yes, it is.
So if you add more, if it takes up more space, what would happen? Where would it have to go? Now, if you're saying temperature is affecting pressure, because again, if you want to say temperature, you lit a candle.
So it's
What
pressure.
will temperature do to pressure?
What's
If
also go-
temperature goes up, what will that do to pressure?
Also goes up, it's a direct.
Also goes up, it's a direct relationship. If you're saying you somehow change the pressure in there by burning the candle, if the pressure goes up, what happens to volume? Goes down. So I'm not saying it is specifically a gas law, but you have to understand that those relationships don't ever change. If you're saying this is changing, we should be able to predict how something else would change as well, correct? So do the experiment one more time. Do the demonstration one more time. Watch carefully what happens to the gas inside the beaker during the experiment. I'm not saying any of those things are accurate or anything. I'm just saying, let's make sure you're understanding what's happening.
Hey, that's what, that's it, that's the last time.
Alright.
What did we say?
There's water in the candle, that's why.
Okay, now please remember, you guys are doing a great job. You really are. Okay? But ask yourself this. If you're saying the volume's going down, so pressure's gotta go up, how do we make
If you
pressure
drain
go
like
up?
half of the candle.
How do we do that?
Okay.
I understand that, okay,
You have to make the walls closer so that.
but we didn't,
Yes, we did, because the water went up.
That's it.
okay?
The water went up.
But it,
then
pressure's causing the water to go up. What caused the pressure to increase? How did we get- So you're saying by the volume going down?
They're in a.
The
gas.
Yeah, because we start learning about all
The
the
question is
gas
which one
laws.
happened first? Because, okay, take that off, just put the thing on it, the volume doesn't suddenly start going down, right?
Okay.
So they both have to be happening at the same time. So if the volume is going down because of something you're doing, how does burning a gas in there cause the volume in there to go down?
Yeah, you
Burn the
know,
whole
it
table.
only has two.
It only has two.
Because part of me still is like, it's because we're burning all the O2 in the container. Yeah. That's what I was thinking.
Think about this, if I give you a hint, how can you ever use that?
Got it. Like maybe that.
Yeah.
That's such a.
You guys are still not done yet?
I don't get that.
We're done, they're not.
So
They stress me
dynamic
out.
fuel plus O2. So yeah, he's.
Oh, it rises, the pressure makes it rise.
Really? So we're saying that pressure pushing down, what's pressure doing?
The volume
What's
is
pressure?
pushing the candle up.
The volume is pushing the candle up.
Yeah. The volume of the water is pushing the candle up. And
Yeah,
it's
after
making
all
it
the.
Okay, now, please listen. You have to think about what would cause the volume, what about the gas in there caused the volume to suddenly change? Because you're saying, what happened inside the container? Let's get that straight. What happened inside your beaker?
Fire.
Fire. Don't care about it, has nothing to do with gas loss.
Or does it?
The what? The water went up. Why did the water go up? Why did the water inside the container go up?
the pressure of the cup.
No. Why did the water inside the container go up? What is the only explanation for the water inside the container going up? About the gas.
What?
The gas's volume had to go down. The gas's volume had to go down because if the gas's volume didn't change, would the water have suddenly gone up? No. So the gas's volume had to change, going down, which caused the water to fill in that space. Okay? Now, you remember the balloon inside the glass container? At the start, what was the pressure like inside the balloon and outside? Equal. That's why the balloon doesn't get any bigger. That's why the balloon doesn't get any smaller, correct? So when you first put that container on there, what would that tell you about the pressure of the gas pushing down on the pressure of the water? They had to be the same. Otherwise, if there was more pressure inside from the gas, what would it do to the water? Push it down. And if the water pressure was greater, it would push it up. Okay? Volume did change. For sure. No question. The volume of the gas became less. What caused that? Which of the other three variables? Pressure, temperature, or amount of gas caused that? And how do we know? By the way, if I'm giving you a hint, you're probably going to want to think about that hint. When you got it, tell me. When you got it, tell our group.
I got it.
Go.
Oh, and I just wanted to tell you, so I'm not wrong in front of everyone.
I've been wrong in front of everybody before. Cynthia said my outfit doesn't even match today, so take a chance.
I mean, the pants are
So,
like
let's go.
bluish and the shirt
So when
is
you
just
burn-
like bright blue.
The thing, right?
Okay,
You
go ahead.
automatically get hydrogen. Because there's no hydrogen in the first
Where are we getting hydrogen? An organic fuel is carbon and hydrogen together. By the way, the hydrogen is in what?
Water.
Water.
Oh, that makes
That
sense.
liquid can't affect it. It's not a gas. Somebody. What about the CO2?
When the fire burns, it burns all the it burns all the oxygen from the air.
Okay.
And
Replaces it with what?
replaces it with CO2 and water.
Okay.
And
Only one of those is a gas, so only one of those matters.
yeah, so the CO2 matters.
Okay. So what does that mean?
It's less. There's less CO2 than there is oxygen. So
There's
because there's less amount, it affects it.
Because it turns the air into water.
The amount
If the amount of gas inside that container goes down,
Chemical reaction.
what else is going down?
The pressure.
It's fire is much. So
No,
you
because
burn
pressure.
oxygen in the air, it
I thought-
H2O.
I don't know.
So it adds the water.
Temperature.
Water.
Now we're just gonna guess variables.
Doesn't go
Not
to-
temperature. Volume.
Stop. Please listen.
Volume, because there's less gas, so it would take up less space.
What happened? What do you mean that's it? It doesn't get any easier than that. There's less volume and there's less gas in there, which means it's taking up less volume.
Yeah.
So the water
Has
goes up and fills in that volume.
And isn't that to keep pressure constant?
Correct. And what else constant?
Temperature.
Good. Hey, guess what? Avogadro's law. Put your stuff back, ladies and gentlemen. Grab a seat. Open your computer. Let's go.
That's not, I don't know what Avogadro is.
He just wants us to say that we use it just why it's my nose still burns from that match. I don't know what it was.
Sulfur.
Yeah, we oh my gosh, you guys, I saw Rose at work yesterday.
Make sure you take the water out of your container before you put it back. I don't want it to spill when somebody goes back and does it with the next hour. Now, again, ladies and gentlemen, I appreciate your effort in giving me variables, giving me things. But again, it comes down to if we're going to say one thing affects another. First of all, we're only going to change two things. You're right. There are times where we could change more than one thing. And we will get to that eventually. But the simplest explanation for what we saw happen here is this. We use up 2 moles of oxygen, gas, to create how many moles of carbon dioxide? 1. So we're using up 2 of these to create 1 of these. All gases, I don't care what kind of gas they are, When they are at the same temperature and the same pressure, they occupy the same amount of space, assuming there is the same amount of gas. The problem is from here to here, there is no longer the same amount of gas. The amount of gas is going down because for every 2 of these that I use up, I only create 1 of these. The amount of gas inside that container is being cut in half. Now, what does that do to the volume? That gas only takes up part of that space. Because the amount of gas is going down, the volume is going down. A direct relationship. We already studied that relationship too in Unit 5, where at STP, 1 mole of a gas occupies. So if we have less than a mole, we have less than 22.4. We've already studied that. Okay? Now, again, maybe you could make a slight case for temperature being involved here. But what is happening to temperature inside that container? How?
It's going up, it's going down.
So you're telling me putting a burning candle inside a container is going to cause the temperature of that container to go down?
No.
And again, I understand, but that's what we got to think about. If anything, if there is a change in temperature inside there, the temperature should have gone up. Okay, what would temperature going up cause volume to do?
What?
If temperature had gone up, what would that have caused volume to do?
Volume would have gone up.
Volume would have gone up. Now, does it make any sense then that that liquid would get pulled into there? No, because if volume went up, it should be doing what? What? Pushing down on it. Maybe you see a bubble come up out of the side because there's no more room for it, right?
Yeah.
But it couldn't have because there wasn't more volume of gas inside there. Okay? Pressure was another one.
Mm-hmm.
If we could have increased the pressure in there, what would have happened to the volume? Volume would have gone down.
Yeah.
How did we change the pressure in there? Did we do anything at all that could have changed the pressure in there? Not really, right? Not really, right?
So because they were changing at the same time, it wasn't.
Well, think of a tug of war.
Oh.
If you have a tug of war, who wins?
Whoever
Person
pulls the most.
The one that is the strongest, right? So if you have 2 variables that are trying to change the volume, which one wins? So in this case, could temperature be the strongest one? No, because it would have made volume go up. Amount of gas was trying to make it go down, and we know what actually happened to the amount of gas, to the volume of the gas. It went down. That's the only explanation we can get. Only explanation we can get.
So that's Avogadro's law?
That is Avogadro's law. That is Avogadro's law. All right, ladies and gentlemen, open up your EISN and go to slide number 39 because I don't believe we got to this one the other day. This is still a Gay-Lussac's law problem, ladies and gentlemen. It is the last one that I'm going to show you, but we're going to review it real quick, talk about Avogadro, and then give you some time to work on some problems today. So this is slide number 39 in your EISN, ladies and gentlemen. Normal air pressure at sea level is 760 millimeters of mercury at 0 degrees Celsius. What would happen to the air pressure if the temperature outside were to be 80 degrees Celsius? Please report pressure in millimeters of mercury and ATM, assuming no change in the volume of the gas. So, ladies and gentlemen, this is a Gay-Lussac's law problem. P1 over T1 equals P2 over T2. We are going to take and we are going to put in our conditions. Now, before we can do anything, what do we have to do with certain things up here? We have to convert 0 degrees Celsius and 80 degrees Celsius into Kelvin. Very good. So we will do that by adding 273 to each. So we get 273 and 353. Any questions on this, on why we're doing this? Good. Now we plug everything into here. The 760 was at 0 degrees Celsius. That goes with the 273 Kelvin. P2 is what we're solving for, and it goes with the new temperature of 80 degrees Celsius, which is 353 Kelvin. Now, again, ladies and gentlemen, how you go about solving this mathematically is 100% up to you. The safest thing for you to do, not necessarily the smartest, but the safest thing for you to do is this point is to always do cross products are equal. It gets it onto one line. There is no chance you will accidentally solve for a reciprocal. But with this problem, there's no way I would solve for a reciprocal because P2 is already on the top. So I'm going to take this and I'm going to multiply both sides by 353 Kelvin to get P2 alone on this side and to get this side to stay equal, because what I do to one side I have to do to the other. So now I have 760 times 353 over 273. Real quick, what's happening to our temperature here? Going up. What's got to happen to our pressure? Got to go up. Pressure better end up being over 760. Do the math, ladies and gentlemen. I get 983 millimeters of mercury. That's one of the two answers that you are supposed to give, because the other one asks for what? ATM. So now you take that 983 and convert it into ATMs by putting one ATM over 760, and you get 1.29 ATMs. It is very possible on a problem, on a test, that I will have you do the problem and ask you to solve it for a different unit. Questions? Yes. Can you wait till I'm done with Avogadro's law in just a few minutes? Okay, thank you. Any other questions on this? Now, in a minute, you're going to be working problems that might be Charles, that might be Avogadro's, that might be Gay-Lussac's. You have to recognize what numbers they're giving you. 760 mmHg, this is a pressure. 0 degrees Celsius the temperature, 80 degrees Celsius the temperature. The only gas law that we have that involves pressure and temperatures is Gay-Lussac's. The only one that involves volume and temperature is Charles. Now be careful. They may give you all three, but then they have to tell you that one of them stays constant. If volume stays constant, it's pressure temperature. If pressure stays constant, it's Charles, volume temperature. If temperature stays constant, it's Boyle's. If pressure and temperature stay constant, it's Avogadro's, ladies and gentlemen. Avogadro's law says the volume of a gas will vary directly to the amount of gas at a constant pressure and temperature. In other words, the more gas you put into something, the more space it takes up. The more space it takes up. Okay? So V and N are in a direct relationship. P and T are held constant, ladies and gentlemen. V1 over N1 equals K. K is still a constant here. Now, here's the one thing I will tell you. It is not always 22.4. The constant is only 22.4 if pressure and temperature are what? More than that. They do need to be held constant. You are correct. But pressure also needs to be at STP. Standard temperature as well. If it is not at STP, there will still be a constant, but it will not be 22.4. So we've been talking about this. That constant exists at that pressure and that temperature, at that pressure and that amount of gas, at that volume and that amount of gas. And if we change them, we'll still have a constant. It will just be a slightly different number. So we can have V1 over N1 equals V2 over N2. The good news, ladies and gentlemen, we very rarely use this gas law. Very, very rarely.
Are you going to make us use it?
I don't remember if it was on the test or not. This is going to come in somewhere else in just a minute. Okay? Questions? So, ladies and gentlemen, 2.236 moles of gas is under conditions that have the gas occupying 1,256 milliliters of space. If the total number of the moles in the container was increased to 0.825 moles, how much space would the gas occupy in liters? V1N1 equals V2N2. Again, units do not matter as long as they are the same on both sides. Milliliters here mean milliliters here. Moles here mean moles here. So, again, solving for V2, I multiply both sides by 0.825 moles. The moles are going up. What's got to happen to the volume? Moles are going up. What's got to happen to volume? What? Has to go up as well. When we're done, ladies and gentlemen, we get 4,391 milliliters. That is what we end up with. Okay? If they were to ask you to put it into liters like they did here, we change it to 4.39 liters. Why? They asked you specifically to put your answer in liters, not the milliliters that you had to work the problem in. Questions?
On our, at least mine, I have the moles on top and then the volume on the bottom.
On your
Yes.
on
ISN.
your EISN?
Oh yeah, me too.
Sorry. Really? Okay. Well, here's the thing that I will tell you, and I've said this before. Okay, I see what I did. I will make the corrections in just a few minutes. With gas laws, it doesn't matter as long as you are consistent. In other words, you could put T over P equal to a new temp over a new pressure. We don't do it because we are trying to create consistency, and I'm sorry it slipped through on your notes that I put it in the other way. In other words, volume in every one of our problems, in Charles' law, in Boyle's law, volume is always on the top. Temperature is always on the bottom in Gay-Lussac's and in Charles' law. We are not going to change that. So for some reason, I changed that on this one. I will correct it. I will do it. It isn't going to show up in your notes. I'm sorry, but I will correct it and I will change it. The good news is, even if you do the problem this way and I do it the other way, if you do your math correct, you have to end up with the same answer. You have to. If we're flipping both sides, it doesn't matter. It is still the same relationship. You are going to get the same answer either way. Questions? Okay, so we've got about 25, 27 minutes left to class, ladies and gentlemen. This packet, ladies and gentlemen, that I gave you the other day, you can now do the problems on the second, third page. You cannot do the combined gas laws on the fourth page. So you at least can do that. Yes. Yes, I'm done now. Thank you for waiting. Go to work on the packet, ladies and gentlemen. If you want a partner, you can get a partner. You want to do it alone, you can do it alone. You want to go back in the lab, you can go back in the lab. Don't waste your time, because to be honest, this is the easy stuff. We're going to get harder, and I don't want you to mess this stuff up because it'll be bad. Yes. At some point I will, tomorrow or Wednesday or something like that, yes. What? Okay, good. You know what? The world needs ditch diggers too. I also really need somebody there to answer me or to ask me the question of if I want fries with that. Okay? Nothing wrong with any of those professions, but if that's what you want to do, that's what you want to do. Go for it.